introduction.
Okay.
Okay, good afternoon, everyone. Bienvenue. So this is part 2 of the CMOS National Speaker Tour for 2021. Last week, hopefully you all had a chance to either see it live or watch it on YouTube. Professor Katja Fennel gave a talk about sort of tracers, does biogeochemical tracers, and their sampling using Argo type floats. So it was a very interesting talk, and this week what we're hoping to do is have a more or less organized question and answer session. And so just as a quick reminder, Professor Fennel is the Killam Professor in the Department of Oceanography at Dalhousie University. I gave a fuller introduction last week, but we will let her take it away and hope everyone gets their questions answered and enjoys this afternoon's event. Thank you.
Oops, I already forwarded here accidentally. Okay, thank you very much, Marek. Yeah, so I hope this will be a bit more of a two-way or multi-way conversation than me monologuing. Looking forward to that. No, it's stuck. There we go. So the first thing I wanted to say is just a quick announcement. In my talk last week, I did refer to a CFI proposal. It was sort of hinting that we are hoping for good news. So today funding was announced for that. So we'll have CFI funding to put a regional array of BGC Argo floats in the Northwest North Atlantic. It's actually announced today during Trudeau's press briefing. Minister Champagne announced CFI funding for this year. So that's good news. The second thing I wanted to get off my chest is just a clarification. So I was participating or audience member in a talk last Friday where somebody referred to something I said last Wednesday in my talk, but I felt misrepresented it. So basically, I was cited as suggesting we don't need chips anymore in oceanography. and the speaker was then asked, do you agree with that? And that's of course not what I said. And that's also not what Marlon Lewis said, who somehow that was attributed to. Autonomous floats will not replace ships. We need ships, right? And just because we have one additional tool at our disposal to make measurements doesn't mean the other tools aren't useful anymore. We'll always need ships. We'll need ships to put floats in the water, to make calibration measurements, etc. Satellite measurements, when they came, they also didn't replace ships. So neither I nor the persons I quoted suggested that we don't need them. So the person who said that actually isn't here, I think, but it's sort of important enough to me to make that point again. Okay, and so now there are 2 questions that were submitted that I'll answer, and then hopefully there are more questions from the audience that we can talk about. So the first one here is as follows. Are there plans to compare the observations from the floats with atmospheric observations over the same locations? For example, near surface observations at the same time as the Tropomi overpass. So I have to admit that I don't know what Tropomi measures exactly. But so my answer is that BGC floats are designed to measure in-water properties, not air properties. There's one slight exception. The oxygen sensor sticks out of the water when the float is at the surface and measures in-air oxygen. And that's done really to check for sensor drift. And if there is sensor drift, it can be used to correct that sensor drift. It's not the best way to measure atmospheric oxygen, of course. So any sort of comparisons would be between in-water properties and atmospheric properties. And I don't know what would make sense there. Of course, if it does make sense, then yeah, somebody should make those comparisons. It's probably not going to be me or my group. The only other comment with regard to the overpass is that we can only control the time of day when the float surfaces, but not where it surfaces, right? Because it drifts passively. So whether there's a match with an overpass will sort of depend on luck, of course, if there are enough floats in the water, then statistically you'll get hopefully enough sort of hits where an overpass coincides with a float location. So that's the first question.
Just to clarify, so Tropomi is a satellite instrument. So I guess the core of the question was seeing if you could sort of align with a satellite passing overhead, and it just apparently, I'm just reading quickly, it gives you you know, limb type view at some atmosphere composition components. So I guess the idea was the person wanted to know whether you could get information about what's going on in the ocean sort of concurrently and co-located with stuff going on in the atmosphere. And I think the Lagrangian nature, as you suggested, of the Argos means not likely.
Well, it depends how wide the swath is and how many overpasses there are, right?
Yeah.
I mean, the hope is for example, for ocean color, I think it's going to be really quite useful. And so again, I don't know, is Tropomi sort of limited in its swath, or is it pretty wide?
Half of the site is in Dutch, so
oh, okay, yeah.
I'm having trouble, but yeah.
Okay, and the person who asked the question isn't here, so it's
Right.
yeah. But I think so. Sort of what I can contribute to the answer is basically on this slide, right? Yeah.
Okay. Anyway, I'm sorry. Just move on. I didn't mean to sow confusion.
That's okay. So the other question was, what underpins biogeochemical models? And it was sort of motivated, especially by the fact that I was pointing out deficiencies. So, and making the point that they are mostly empirical based. So what are they actually based on? And so this, I have multiple slides here. So I'll take a little bit longer talking about this. And then it's open for questions from you or comments. So biogeochemical models, let's start with the first principles that we have in order to formulate the biogeochemical models. There's conservation of mass. So the number of nitrogen, carbon, phosphate, oxygen, silicate, iron atoms should be conserved. Right? Mass conservation is one first principle we have. And then there are some stoichiometric relationships. For example, the oxidation of ammonium to nitrate. We know what the stoichiometry has to be, how many oxygen atoms are needed to oxidize ammonium to nitrate. So there's some reactions in these biogeochemical models where we know exactly what the stoichiometry is. And that's it. Then there are lots of empirically based choices that have to be made in formulating a model like that. Very different really to, you know, if we try to contrast it to circulation models, where we have Navier-Stokes equations, where we don't really discuss what the important state variables are. We know what the state variables are for a model of atmospheric or ocean circulation. It's a bit different story for the biogeochemical models. Oops. So the empirical choices include which elements to include in the model, right? Of these here, which ones should be included? And so in climate models, all of these are typically included. So it's a pretty long list, actually. A step further, what state variables actually have to be included? And that's, of course, determined a little bit by the choice here of which elements. But then there's this additional challenge of taking communities of organisms, microorganisms, phytoplankton, heterotrophic organisms. They are very diverse. And so we somehow have to lump them into what's called typically functional groups. So we lump them into units that we think are functionally somewhat similar and homogeneous. So for example, 2 to 3 groups of phytoplankton, 2 groups of zooplankton, should be two or three groups of detrital matter, and then of course the inorganic species, right? Nitrate, ammonium, phosphate, silicic acid, dissolved iron. So it's not a priori clear what those exactly should be. What should the state variables be? It's somewhat an empirical choice. So once that's defined, once you sort of have defined what state variables you want to have included, then the flows between these state variables, or you could think of them as pools of matter. So then the flows between them have to be parameterized. And again, there are no real first principles. It's based on empirically derived functions, typically saturating functions, but there are many different functional forms. And one has to think about switching behavior, how that's parameterized, right? If you have a group of zooplankton that is able to prey on different groups of phytoplankton, for example, or phytoplankton need to take up different inorganic species to grow biomass and carry out photosynthesis. So again, lots of choices here. And then lastly, the parameters governing these parameterizations, right? The growth rates, the loss rates, half saturation concentrations. There are lots of parameters that govern these flows between pools that also have to be defined. And these aren't well known either. So I think you can immediately see there's a lot of empirical choice, which of course also means there's lots of sort of uncertainty, that many different ways one can go with this. So let me give you a very simple example of a biological model, sort of almost the simplest we can come up with. And it's typically referred as an NPZD model because it has a pool of nutrient, one pool of phytoplankton, one pool of zooplankton, and one of dead organic matter, detritus. So shown schematically here. So 4 pools, and then the arrows that sort of determine the flows between those pools. So that's pretty simple. And just writing the equations down for that, gives you these 4 couple differential equations. Number of parameters here, right? All these L's. The more parameters hidden here in these functional relationships. So this is already pretty rich in nonlinearities and in parameters. And this is really rather almost trivially simple compared to what you need in order to really set up a global biogeochemical model, because you need multiple functional groups for phytoplankton and zooplankton and multiple elements. And then there are, of course, the choices of parameterizations, right? So just trying to put a visualization on what I said on the previous slide. So I said they're typically saturating functions, but there's slight difference in the functional forms that then affect how the model behaves. So for example, here the red one is called S-shaped curve, right? Because it has a little bit of an S shape. The blue one is more like a standard Michaelis-Menten curve, first order parameterization. So the modeler who is deriving the model or is defining the model has to choose what parameterization, what functional form for which parameterization, and then the choices of parameters, right? So here's the same functional form, but for different parameter choices. And so this schematic here now has many more state variables and many more flows between them. And this is sort of what a typical medium complexity climate model looks like. This happens to be Piscis here. So that's built into the French Earth system model. And sort of the Earth system models by other nations have similar biogeochemical ocean models. And each of these bubbles here is another state variable, right? And you see all these flows, and now, keep in mind that there are parameters governing all these. So it's a bit daunting, right? Considering the nonlinearities and all these unknown aspects that go into it. And so most climate models, the biogeochemical components look sort of like what I showed you on the previous slide, but there's no consensus that that's the right thing, right? That in fact, there are sort of different directions in which people go to modify them. And they're basically diverging. So we're not even in agreement as to which direction we need to go to improve models. So one direction is to go to much simpler formulations. And one example is Bling. That's a model that Eric Galbraith, while he was a postdoc at GFDL in Princeton, developed. And he stripped it down dramatically to just 3 state variables. Only phosphate, oxygen, and DIC. And all the other sort of circles and boxes here, they are just diagnostically derived from these concentrations. So extremely highly simplified. And they did couple that to the high resolution GFDL simulation, the CM 2.6, really high resolution for a climate model that they ran for like 100 years. So that's one direction. The other direction is to go much more complex. So this is an example here of the Darwin model. That's something that Mike Follows at MIT has developed a number of years ago now, and that's been received quite positively by people, especially with a more ecological bent. And there he's taking it much further, right? Where a climate model maybe would have 3 to up to 5 different phytoplankton groups, and they're labeled here as picoplankton, coccolithophores, diazotrophs, diatoms, mixotrophic dinoflagellates. So where a climate model might have 5 functional groups, in their model, they actually have many, many functional groups for each of these subgroups for each of these functional groups. And they are then adapted to cold or warm, and they range in size. So it's drastically the other direction, right? Many, many more tracers. Oops. Of course, computationally, a bit of a nightmare to do that. Yeah, so, basically in biogeochemical modeling, there are lots of open questions. It's really rather empirical. And the only way forward, in my opinion, is to get better observational constraints, because there's just no hope that somehow by accident we get it right. We need observations to constrain what's going on. And maybe I leave it there. That was the last slide here that I had prepared, and the second question that I had. And maybe turn over to you and ask if there are more questions, or if there are comments. Maybe somebody has something to contribute.
Okay, thank you, Katja. That's great. So I'll throw it out to the audience. I mean, if people do know how to raise their hand, it's in the reactions part of Zoom. We could do it that way, and I could call on you. Or since it's usually quiet at the beginning, I think if you're the first person who wants to say something, you can just say something. But don't forget to unmute yourself as well.
Hi, Katja, it's Blair.
Hi, Blair.
So is there discussions within the biogeochemical modeling community how you would actually assess, even if you had, a good observational data set, how you would actually assess whether your models are working well, or simulating the truth? Like in the physical community, there are, for atmospheric models, or in the ocean, there are standards by which I think the modeling community uses to assess the goodness of fit of the models. Is there such a framework in biogeochemical modeling that is analogous?
I don't think yet, but that's obviously where it's going, right? I anticipate we'll have sort of a rigorous framework for model intercomparison, and that will be really interesting. So, and that hasn't really happened yet, partly because the observations weren't there, right? But now the observations really are starting to come. So I think this is that's something I'm really interested in, and from my point of view, it's one of the high priorities. And we actually have already sort of taken some steps to prepare a workshop There's some the OFI project that we have funded. There's some workshop money earmarked for that type of exercise where we bring in different global modeling groups. So hopefully we can move forward when travel restrictions ease a little bit, or it has to be remote, but it's an obvious important thing that we have to move in, direction we have to move in. And
Okay,
I think we'll actually look closely at what other fields that you've mentioned have done, and learn as much as we can in those approaches.
okay, thank you.
Hi, Katja, it's Chris.
Hi, Chris. How are you?
Good, how are you?
Good.
I wonder, so Argo obviously wasn't maybe conceived with VGC modeling in mind, and so there's maybe some things that like floats could provide or Argo could provide that it isn't, just because it's not in the, maybe like historical framework of it. Like timing is what comes to mind for me. Like it exists, but it wasn't sent for a long time because we didn't know that. And so I wonder, just like from a modeling perspective, if there's anything that you run into where, you're trying to use a float to supplement or assimilate into a model, and there's something missing from Argo data where you're kind of like, well, it'd be really nice if we had this from this data set or not.
Well, I mean, to those of you who don't know Chris, who just asked a question, Chris is a former student of mine, and he's worked on trying to get productivity and respiration, community productivity and respiration out of Argo float observations that was sampling a little bit different sampling regime. And so to me, that's one of the interesting directions, Chris. I'm still interested in that. And I know that many other groups are too. So getting at rates in addition to, the sort of the most important state variables is one really exciting direction. And another, so in addition to the production and respiration, there's also the vertical carbon export, right? So export events, observing export events directly is kind of really interesting, a really interesting direction. And so the work that Nathan Briggs has done on that, but also other people in the UK, so Giorgio Del Olmo comes to mind. There are many really interesting directions that one can go that are a little bit maybe a distraction from the main Argo mission of providing climate quality data for global change questions, right? That's the core mission. Right. And so the Argo steering team will always try to hold everybody to that mission as the first and most important goal. But there will also be hopefully flexibility to explore other things, maybe not at the global scale, at the complete resolution, but in a process study type kind of way, which is what we are planning to do with the CFI project.
Thanks.
But so Chris, if you have any ideas, yeah. I would love to hear.
Sounds good.
Hi, Katja. Could I ask a question? It's Vince here.
Please, do you maybe, could you speak a little bit louder?
Oh, sure. Yeah. So I watched the talk. It was great. Thanks. Every time I listen to my colleagues in oceanography, I learn a little bit more about the tech I'm trying to develop for. Just looking at the Goose and the EOV, what gets onto an Argo. As you know, we're working on the phosphate sensors, and we're getting pretty good data out of a football-sized device, but I somehow still feel that that's a little big for an Argo. Yeah. And looking at nitrate and marlin's trajectory and seabirds going from sort of a few BGCs to 50 to a couple hundred to, circa 1,000. Do you have a feel for how long that took? And, you know, if a person was doing that with, even if you had an all optical phosphate sensor, let's say, what is still a trajectory historically to go through that kind of a roadmap? Is it like 10 years, 15 years, or how? I don't have any insight in that. How does that get validated? How long has that taken in your experience to get a sensor sort of vetted to be one of the key 6 or 7 on the BGC program?
You know, I have a feeling that it could go relatively quick these days.
Mm-hmm.
Yeah, so I mean, on the sensor development side, you are the expert, right? I can't comment on how long, you know, that takes.
Mm-hmm.
On the sort of field proofing and demonstrating the robustness, I have a feeling that a few years are all that it takes.
Oh, that would be exciting.
I mean, some obviously have, I mean, oxygen has been around for such a long time. It's such a well-tested sensor, right? That explains why it's so widely used.
Yeah.
But some of the newer ones, I mean, pH hasn't been around that long, right? And it's, there's still things to be figured out. But it's such an important a quantity to get inorganic carbon variables that, you know, if the need is there, people are willing to, like the desire for uptake is there too.
Well, thanks. We're excited to work with you in the coming years, and congrats again on the CFI.
Thank you. Yeah, I'm looking forward to.
Katja, could you maybe just say a bit more about, now that the CFI project is funded, a little more detail on what you're planning to do? I know in your talk last week, it was sort of one slide, if I recall correctly, with just some sort of broad statements, but maybe, you know, are you planning to do new sensor development that Vince has referred to, and you know, what you're hoping to get out of that project?
I'm trying to, trying to bring the, yeah. So maybe I can go to that slide. Here we go. Oh, yeah, it's this one. So so first of all, I should say that the CFI funding, so CFI only funds infrastructure. So there's no research money in here of any sort. It's only infrastructure and the installation of the infrastructure. And so that means there will be lots of proposals written to fund research to actually use the data. And I hope that's not only us, right? Because the data is freely available. So I hope that many groups in Canada will do that. The sensor development that Vince has referred to. So Vince, please jump in and correct me if I'm wrong, but I know that Vince is one of the PIs on an OFI project that's led by Zoe. So there's funding to work on the phosphate sensor, Vince, right? Is that correct?
Yeah, that's correct. Yeah, well, sensor development's decently expensive, so I've been grabbing lots of money wherever I can. But
exactly,
you know, the CFI is, as Katja mentioned, the way I've been looking at it is, it would be nice to, you know, understand or have maybe access to 1 or so units, but that's something Katja and I will talk about. But there's no research funds for that out of a CFI.
Yeah.
It's only out of the OFI that I've been funded for phosphate.
Right. And so again, Vince, correct me if I'm wrong, but so the plan is to first test it on a mooring, right? Where you have power supply, where you can get it back, where size isn't quite the issue.
No, we don't want to make it too hard for ourselves. So we're going to go where power is not constrained and size is not constrained. And Katja can tell me I've done a good job or a poor job on a mooring. And then if it looks like it's scalable, then maybe in a year or two we'll look at something like that. That's kind of been my vision, but I'm really looking to Katja and Zoe for insights into that.
Yeah. so that's sort of the sensor question. So on this slide, I do have some, maybe we go to the infrastructure development section at the bottom of this slide. So this is here, the first one is one that sort of relates to the question Chris asked, you know, what other measurements could we potentially make with the Argo floats? And so the rate measurements, net community production, net community respiration and export, right? That's really exciting. And so Bin Wang, who's also on this call, is actually working actively on that right now with the respiration, trying to get respiration and sort of export length scales from existing Argo data. So they're quite interesting possibilities. Then we want to work on developing products, extending ocean color observations into 3D. So Blair, this is something where I would definitely sort of look to also Emmanuel Devret, working with Emmanuel. I think there's sort of a hierarchy of products we can envision, some that we can develop relatively quickly, and things that take a little bit more effort in algorithm development, but definitely that's something I'm interested in, you know, and it also, initially we might have climatologies for our regions for nutrients and pH and oxygen that will get better the more observations we have, and the better able we are to merge it with models that hopefully also will get better as we have better constraints. And then the third one here is we do want to build an assimilative model for the region. And again, we have already OFI funding for model development. So in collaboration with Jinyu Sheng's group, we've begun, oops, sorry. We've begun setting up a regional model here for this. So it's centered on the Labrador Sea, but includes also this region here. And so the plan is to assimilate the Argo data, which is, again, it's something that Bin Wang has already done with more limited Argo data in the model in the Gulf of Mexico. So we're keen to get that going here. And this is obviously sort of a bigger task. And these are all things that are mentioned in the CFI. So these are concrete plans in the CFI. Again, you know, emphasizing that there's no research funding coming from that project. So we have to find any research money to do this, we have to find elsewhere. And then sort of science questions that we're interested in. You know, there's obviously the carbon sequestration and ocean ventilation question, right? So it's convection in this region is really important for that. Those two processes, right? Bringing carbon into the deep ocean, supplying oxygen to the deep ocean. And this region here is a choke point for sort of the global deep ocean circulation. It's very sensitive to changes in climate, right? So we know that deep convection is quite sensitive. You know, melting of Greenland ice could have big impacts. Warming could have big impacts. Trying to sort of get the models to reproduce these processes better is going to be an interesting challenge, but really useful if we make progress here. And that hopefully would also have positive effects on sort of the climate modeling community. And then, so the second bullet here, rate of change in ecosystem productivity, oxygen loss, acidification. I mean, that's, you know, obviously we want to sort of monitor and document what's changing in our region. And the last one here, right, we do want to assess how climate models, that actually goes to your first question, Blair, I think. So we really would like to focus on intercomparing models in our region and against the data in light of these new data sources that we'll have to pinpoint maybe where some things go wrong, where some things can be improved. So yeah, does that sort of give you an idea, Blair? Or maybe keep on asking what you're wondering about.
I don't want to dominate the conversation here. I think we could talk, you and I could talk for a couple hours. So, yeah. But I do have a question, like what your linkage is to the work that Marcel Babin's group in Laval has been doing in Baffin Bay. They've had biogeochemical Argo floats in Baffin Bay for the last 4 or 5 years, and they're planning to deploy again this summer. So I'm just wondering does that tie into the modeling you're doing? Does your model extend into Baffin Bay?
So it does. It doesn't have an ice component yet, but that's Eric Oliver's group is working on that. So yeah, we still have a lot of ways to go, right? But absolutely. I mean, I don't see it as an immediate. I don't see an immediate strong link. Obviously, having access to his data is going to be really interesting and useful. But we probably want to get the ICE model to run, which maybe in a year we have that. Then it would be really useful, right, to draw on these observational data sets below the ice. Yeah, and as you know, Marcel is a co-PI on this project, so I mean, he's also very busy, but he is interested in this stuff. So I'm hoping we can get a sort of a little bit closer collaboration going when there's some interesting stuff to talk about. I think that's what it will take to draw him in and get him interested.
Okay, one last question for me, and then I'm gonna stop. Can you comment on how much you think having good biogeochemical data in these offshore regions, off-shelf regions, can benefit your models on the continental shelves and slopes? Because from a fisheries perspective, almost all of our fisheries are on the continental shelves. They're not in the deep ocean. So I'm curious as to, from your experience in modeling, if you have better boundary conditions, I guess, in the offshore, how much will that influence or improve your models on the shelves?
So I'm hopeful that it will have a really big positive impact. And so I'm going to give you an example, and this is sort of based on work that Kristen Rutherford, who's also here, a current student of mine, based on her work. So Kristen is working on a regional model here for the Northwest North Atlantic Shelf and looking at carbon fluxes. And so a little bit of a background is that generally shelves in mid to high latitudes are thought to be sinks of CO2. Now, Blair, you are familiar with Elizabeth Shadwick's work, right, and Helmut Thomas's work, which showed this relatively big outgassing here on the Scotian shelf.
Yep.
Right. And so it's been a puzzle for quite a while. And then there were all these follow-up studies by other groups that were like, it's a sink like everything else, right? And so Kristen now, and we have one additional observational constraint now, in addition to this time series here on the shelf. Now, Doug Wallace's group has a transect here on a ship of opportunity, a supply ship that goes to Sable Island. So they have a PCO2 sensor on that. So we have additional inorganic carbon data from this transect like twice a week. And so, the model and these two local observational sources, data sources, show that this region is a source of CO2 to the atmosphere. In contrast really to other coastal regions in that latitude band, and in contrast to expectations. And that's because it's this carbon-rich water in the Labrador Sea, cold carbon-rich water in the Labrador Sea that moves onto the shelf here and then travels along. And as it travels, it warms. And as carbon-rich water warms, it becomes oversaturated and CO2 gases out. And of course, there are biological transformations too. But so the model nicely explains what was a bit of an enigma, right? So Elizabeth and Helmut couldn't explain they couldn't really explain well why there was this outgassing, right? They talked about upwelling, but actually it turns out that CO2 is even lower here in the off-shelf region. So it couldn't be that. Plus we know that there's a shelf break frontier distinction in water mass properties, right? So they haven't been able to really to explain it. Now the model nicely shows it, right? So if you have the right boundary conditions here and here, And if you have some confidence in the model's ability to simulate the coastal circulation, you do better. And I think we could hope to extend that to nutrients and productivity too, right? If we get good boundary conditions here, hopefully those other variables will also be improved. But so this work that I just described by Kristen makes me optimistic that, yeah, having better boundary conditions will help on the shelves.
Okay, thanks.
Of course, we also want data on the shelves, right?
Okay, maybe at that point I can ask my question. So I'm typically a shallow water guy. I was wondering, is there any hope of something like Argos that could be released in the Great Lakes or sort of in fjords or more coastal settings? I know the Finnish Meteorological Service does something in the Baltic, right?
Mm-hmm.
But that's the only thing I know of.
Yeah, I mean, I don't see why they couldn't be released in the Great Lakes. Of course, you probably would want to retrieve them sooner. So one issue with floats or with any sort of autonomous instruments that are in the ocean for any extended period of time is fouling, biofouling. And so so Vincent can jump in at any time, right, and contribute to that issue, or anybody else who has experience with that. And so the reason that it seems to work really well with BGC Argo is that the floats spend a lot of time in the deep ocean where it's cold and dark, right? The surfacing time is relatively small, is a relatively small fraction of their lifetime. And so that's why biofouling hasn't been a stumbling block or fatal issue for these. Anything that you have on a mooring in the surface needs to be dealt with like every 2 months and cleaned off, which obviously isn't possible, right? We can't clean off the BGC floats. So if you were to deploy something in the Great Lakes, I think that would be a question, right? The trade-off between deployment time, like length of deployment, and biofouling. And so I admit I don't really know how deep the lakes are and how much activity is sort of at greater depth there.
Yeah, I mean, I guess I was thinking of Lake Superior, right, which is the deepest. So that I wouldn't want to put them in Lake Erie, which can be really shallow over
Yeah.
at least one of the basins and probably two, but Lake Superior is a lot deeper.
Yeah.
And then I guess I would imagine because it's colder, the issue of biofouling could be mitigated. But yeah, I mean, I guess practically speaking, I would bet funders would be reluctant to put things that expensive things like Argos into environments where you might, you're more likely to interact with shores, right? I mean, your dots on the slide you have up.
Again, since they spend most of the time at depth, there isn't really much of an issue with them running ashore or running aground. So I do know that Environment Canada, colleagues at Environment Canada have deployed them in Gulf of St. Lawrence and gotten really interesting data, and were quite enthusiastic about that experience. Greg Smith, I don't know if you know him in Montreal. Those were core Argo float. Well, maybe we shouldn't call them Argo floats. Obviously, they weren't part of the Argo program, but they basically bought an Argo float and deployed it in the Gulf of St. Lawrence, and were quite enthusiastic about the data they got. And so I would also say, the core Argo floats are a lot cheaper than the BGC floats. So, I would start with 1 or 2 of those. And Blair would know exactly how much they are.
Well, one float is about $25,000. I guess Merrick, it would depend on the science question you're trying to answer in the Great Lakes. And there are other autonomous options like gliders that might be a better solution because they're recoverable. You can somewhat control their flight path, and they can go out for several months at a time. But they're about $250,000 a piece. So it really, I guess, would depend on what the questions being asked are, what the right technology would be to apply in those situations.
Thanks, Blair. Yeah, I know Jay Austin said really good luck with gliders, sort of out of Duluth. I guess I was just thinking, basic questions, right? I mean, how much do we really know about deep water circulations, right? So there was a sort of fascinating article about why Lake Superior and the Gulf of Mexico are so different from one another, even though they're sort of comparable sized bodies of water. So that's what I was thinking of. Nothing specific. I'm not ready to write anything, but I appreciate both of your answers. Thanks. So we're doing well. Can I just encourage a few more? We've only got about 10 minutes left, but we've had a good discussion going. So do we have anything more from the broader audience?
Thanks, Vincent, for the clarification, your question or your comments and questions today. That helped clarify things earlier for me anyway. And in terms of the parenthetical comment I made, I also don't want to be misinterpreted, not to be referring to the truth, as Blair says. This is our reference. It's just that with measurement, with satellites and models and observations of all kinds, there's nonlinearity with reference to what's going on in the ocean. That anyway, I just wanted to clarify that as well.
Okay, so I'm not seeing a wealth of response.
David Greenback has his hand up.
Oh, there it is. It just showed up. Oh, sorry. It takes a while to shuffle. David, go ahead. I think you're still muted, David.
David, we didn't hear anything. If you were speaking, we missed it. You're muted, it looks like. No, now he looks unmuted, doesn't he?
Yeah, it does not look muted on my screen, but
no, you're right. It doesn't.
Perhaps you could put your question into the chat.
I wondered if you maybe just walked away briefly.
Oh, you may have.
Okay, can you hear me now?
Now we got you.
Yes.
Okay, just a minor comment on some of the observation bits that are coming up, and I can't recall whether you mentioned it in your talk, and that is the SWOT, SWOT satellite that is coming up in the future. And it has some very high resolution sea level measurements coming, and also with very high resolution near land. So if you're interested in lakes and rivers, let's see if I can find, well, for land, they've got a 2 kilometer by 2 kilometer sort of measurement that's repeating every 21 to 23 days. And no, I had it here a second ago. I think they're talking about 70 meter spatial resolution of 70 meters for elevation inland near water for hydrological type things. So there will be some satellite surface elevation stuff coming up that could be very, very useful. It's sort of a repeatability, I think 23 days. But it will be a fairly decent wide swath picture that you're going to get, a snapshot of not just a point, but of some sort of area or line that you're getting. And so just so that if you're not aware of that it might be something to look forward to.
Yeah, definitely.
Okay, thank you, David. So do we have anything else?
Can I ask one more?
Yeah, of course.
Okay, so engineer speaking, just I'll preface that. We have nitrogen or nitrate, ammonium, etc. Many of the main nutrients, phosphate like that. What would be the guess of the next most useful parameter to measure on autonomous platforms for sensor developers? Looking forward, you've got really deep knowledge of the models at play. What do you think I should be developing 20 years down the road?
I think a second sensor for one of the inorganic carbon variables, because I mean the carbonate system, of course, is of very high interest and relevance because of the CO2 fluxes, not only between atmosphere and ocean, also what happens in the ocean. And the carbonate system is sort of this nonlinear combination of different carbon species. And then there's four variables in total, basically. The conservative ones that are included in models are DIC concentration and alkalinity, but there's also pH and PCO2. There are also the concentrations of the carbonate bicarbonate ions. And so in order to constrain these variables, so in order to calculate PCO2, for example, at least two of these carbon variables have to be measured. Right now, we can only measure one autonomously on floats, and that's pH. So getting a second of the carbonate system variables would be really, really useful. The way it's done right now is that basically alkalinity is inferred from measurements of salinity, and then oxygen and nitrate are sort of used as environmental correlates, and then based on like real in situ alkalinity measurements, just a regression is developed between the measurable variables and alkalinity that's then used. So last week when I showed the ASC flux work by Alison Gray, those fluxes were estimated based on the pH measurements from the floats, and then estimating alkalinity based on sort of in an indirect way based on salinity, nitrate, oxygen. And that then allows to calculate PCO2 and estimate the ASC exchange. So getting this, and I don't know what the lowest hanging fruit is there. Probably PCO2, because there are already PCO2 sensors, but not miniaturized for floats yet. I think that would be a big one.
Great. Oh.
And then the other direction is, of course, optical imaging. So these techniques where images are taken that can then be analyzed, for particles and even down to like individual organisms. So that's a bigger, sort of the bigger in terms of size range, bigger particles. But my guess is that's less your wheelhouse. I think, yeah, carbon variable.
No, it's wonderful. Thanks. Yeah, I've done some plasmonic and vision sensors, so there might be something there.
Oh,
I'd like to follow up with you. It's, as always, Katja, I learn a lot every time I listen. So thanks, appreciate it.
Okay, so in the interest of time, let me sort of say last call at this point for questions. David, your hand is still up, but I'm guessing that's a remnant of this.
It's a remnant. Sorry about that.
No, that's all right. I just learned about the hand on Zoom earlier today. So, so do we have any last questions for Katja? Okay, well, so with that, I have one more request for everyone, which is to publicize Katja's public talk to any school teacher or your sort of high school aged or sort of pre-university people you may know. I know a few. I may advertise it to them. In fact, I will for sure, though my kids don't really listen to me, but that's okay. I'm sure I'll find some takers, and hopefully we'll reconvene for part 3 of what's been a superbly interesting event. And so I'll thank Katja again. Weird clapping over into the ether, but so take care, everyone, and I'm sure if there are further questions, we can arrange to have those delivered, or you can use the magic of the internet to ask Katja directly. And of course, congrats on the CFI and the old saw, right? You get all the money for equipment, and now you have to figure out how to fund the people. So good luck with that.
Thank you everybody for sticking around and for participating.